let's see, to kind of kick this off, I'll do this, no, just add one. Okay, so I know it says something about a loon, blah, 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 but let's do this sort of factor label problem. What if somebody, let's say your car, you are driving down the road at 35 mph. Yeah, you guys don't have this slide. Say you're driving down the road at 35 miles per hour. Must be in town or something, okay? Of course, we talked about anytime you hear the word per, think of slash. So really what that means is 35 miles per 1 hour. That's what it means. That's totally what it means when you're driving 35 mph. Okay? So, for instance, at this speed, how far would you be in 2 hours? You would be 70 miles down the road. Exactly. Let me show you how you did that. Let's see. This, by the way, is kind of a physical property of your vehicle, 35 mph, 35 miles per hour. It's kind of like a done in it. That just happens to be how fast you're going at that time. It's a property. So when I asked how far, if you give yourself 2 hours, you guys told me you would be 70 miles down the road. Okay, this is what you guys did. You guys basically took your 2 hours, you put it over 1, and then you multiplied by how fast you were going. Just straight up, not the flip or anything. 35 miles per 1 hour. And it goes back to what we were talking about earlier in here about factor label. So do you see how the hours cancel? Okay, and you're left with units of miles. And so the units are miles, and you guys took 35 times 2 and got 70. Okay. Now I'm not going to worry about how you round this because I didn't know if it's 2.0 hours. I didn't know it was right at 35.1 miles per hour. Okay, but that's exactly it. Well, what if we were to do kind of a similar problem, and I were to ask you how long will it take for you? And to me, I'm going to have to use a calculator for this one. How long will it take you to get 50 miles down the road? And I can't just look at that. 50 miles down the road. I'm going to tell you, though, in order to do that, you're still going to use your physical property of how fast you're going, and you're going to go 50 miles down the road. That actually is going to be your first term. But do you see, if we want to go ahead, and this is MI there. Okay, this is miles. If we want to get to hours, do you see where we're going to actually have to flip the 35 miles per 1 hour? That's to say, if I go ahead and insert this down here, but I flip it, I go in 1 hour, I will have traveled, going at the speed, 35 miles. The beauty of doing that is what happens to the miles. They cancel each other out. Yep. And like I said, here's where I'd have to get out my calculator. Just for kicks, I'm going to go ahead and put a decimal after the 50 miles. You know, I said, how long will it take you to go 50 miles? I'm going to say, how long will it take you to go 50 with 2 significant figures miles? So I'm going to grab my calculator here. The fact that I put a decimal there means I have 2 sig figs in the first term. I'm going to go with 2 sig figs in my speed. Okay, and if I take 50 divided by 35, I'm only allowed 2 significant figures. So I got 1.4 units would be hours. 1.4 units are hours. That's the answer to that problem using the factor label method.
It's really strange.
What's that? Yeah, it feels strange, and sometimes you're like, it feels overly complicated.
Well, it's just because it takes it. Oh, never mind. I was going to say, because it's 2 hours to get 70 minutes, is 1.4 to get 50 minutes. It seems like it should be, I don't know, it just doesn't seem right.
How long will it take you to get 50 miles? What you're doing is right. You're kind of thinking through it. Does this seem reasonable? And
I guess it's reasonable if the calculators put it out, but I was thinking something
yeah, yeah. So back to your your notes and stuff. So we can use like speed. Speed is basically change in distance over change in time to get back and forth between time and distance. And so here we're picking on a bird. We're saying the bird flies 14 meters per second, which is pretty darn fast. A meter is like a yardstick, so 14 of those in 1 second, which I've never looked this up. I know. Does it seem reasonable? If we're going metric, meters is metric. So how long in minutes will it take the loon to fly 5.00 kilometers? Now, right off the bat, you're like, grr, my distance is in kilometers, but my speed is in meters per second. So right off the bat, we're going to have to actually kind of do a little conversion there to get from kilometers to meters. But after we do that, we can actually then use the 14 meters per second as a conversion factor. So anytime you are faced in a problem with something like 14 meters per second, what I'd like you to do is, in order to get ready to use it as a factor label problem, work it out that way, is unpack it. So 14 meters per second unpacked looks like this. It means at that particular time, that particular loon is flying 14 meters in exactly 1 second. So when we unpack 14 meters per second, there's no uncertainty brought by the 1 in the 1 second. The reciprocal or the flip is true. For that particular loon in 1 second, it will fly 14 meters. We could also kind of flatten it out and make it an equality for that particular loon at that particular time. 1 second is equal to 14 meters. So to do this, like I said, one kind of grr right up front is that darn distance that we're given, and we don't know how long it will take, is given in kilometers, not meters. So we got to fix that. And of course, we kind of talked about that within the metric system. Kilo means 1,000 times. So 1 meter is equal to 1,000. 1 kilometer is equal to 1,000 meters. Okay. Then actually, we can go from meters to seconds at that point using the speed of the loon. And unfortunately, we've got one more twist on this. It wants time not in seconds, but it wants time in minutes. So, of course, what's the relationship between seconds and minutes?
60 seconds in a minute.
Yep, 60 seconds in a minute. Yep, you got it. So kind of the strategy to work this problem. Now, some problems, there's more than one way to work it. And probably there is even this one. So the first term is going to be that 5.00 kilometers over 1. Then we want kilometers to cancel. So how are we going to use this equivalency statement? How are we going to use that to our benefit?
1,000 meters on the top, 1 kilometer on the bottom.
Yep, 1,000 meters on the top, 1 kilometer at the bottom. Very good. Cool. And now we're going to go ahead and use the speed to have meters cancel. What does it look like?
14 meters on the bottom and 1 second.
Yep, 14 meters on the bottom, 1 second on top. Perfect. And then we want our seconds to cancel when we're left with minutes. So what's that last one look like?
60 seconds on the bottom, 1 minute on the top.
60 seconds on the bottom, 1 minute on the top. And then as we've set it up, units of kilometers have canceled, units of meters have canceled, units of seconds, this is my favorite part of the problem, units of seconds have canceled, we're left with units of minutes, which is exactly what we were after. So let's see, do you guys remember metric brings, within the metric system, no uncertainty? There is actually, I put a question mark over here, there actually is uncertainty in how fast the loon's flying. Remember, we unpacked it by definition per 1 second, so there is uncertainty here. I got 2 sig figs here, and there's no uncertainty in within the time. So how many sig figs do we need to round it to? Not 3, 2. Yep, only 2. Yep, you got it. So hopefully you come up with something like this. Like I said, every once in a while my slides are wrong, but this one I think is dead on. Okay? Did I both skip the last example? Nope, don't skip the last example. So in lab tomorrow, you're going to be using Bunsen burners. You're going to be heating up two metals. You're going to be heating up aluminum and copper. And the thing about metals is they suck up energy differently. Okay, it's like a physical property of the metal. So this one says if it requires 40.7 kilojoules of energy to go ahead and vaporize 18.0 grams of vaporize 18.0 grams of liquid into a gas for water. Okay. What happens if you scale it up and instead of 18.0 grams, you have 150 grams? So this is what it looks like. Okay, so here's my liquid water, and it is 18.0 grams, and I'm going to zap it with 40.7 kilojoules of energy, and it's all going to gasify. What if we scale up our liquid, and now instead of 18.00 grams, it's 150 with 3 sig figs grams? Okay, so the question here is how much energy. So you figure it's going to be more, right? Okay. This actually, we can't scale all things in chemistry, but we can definitely, or physical science, but we can definitely scale this one up. So to work this, there's another twist. The last twist is basically we don't want energy in kilojoules, which will be not too bad to get to. We actually want units of energy in calories. And here's the relationship between a joule and a calorie. Now I wish I had skipped this one. I usually do. Okay. So when it says that this amount of energy is required to vaporize that mass of water, actually we can set that up as a physical property of water. It's called the heat of vaporization. Okay. We can set it up that way. We can flatten it out. We can actually also flip it. So these are all fair game for the physical property of water. Vaporizing liquid water into a gas. So then to work this, what we're going to do is we're going to start with the mass of the water, the scaled up mass of the water. Okay. We're going to go ahead and use our relationship about how much heat it took to go ahead and vaporize 18.0 grams of water to get to heat or kilojoules of energy. Then we're going to go ahead and convert that to regular flat old joules. Okay, we know a kilo and a regular old joule has this relationship. In 1 kilojoule, there are 1,000 joules. And last but not least, within the whole energy thing, we're going to skip from metric to English. So we're going to go from joules to calories with that relationship that was given in the problem. With regard to energy, and that's an exact relationship. With regard to energy, 1 English calorie is exactly equal to 4.184 joules. So that is exact. All right. So here we go. Starting with the mass of the water, 150 with 3 sig figs grams of H2O over 1. Then we're going to go ahead and pull the relationship that was given. Now, if we want grams of water to cancel, what's our next term going to look like?
40.7 kilojoules over 18.0 grams.
Yep, 40.7 kilojoules over 18.0 grams. Perfect. Now, this was a step where we're trying to go from kilojoules to joules. What does that look like?
1,000 joules over 1 kilojoule.
Yep, 1,000 joules over 1 kilojoule. And last but not least, we're skipping from joules to calories. So what does that last one look like?
1 calorie over 4.184.
1 calorie over 4.184 joules. Exactly. So looking at how we're going to round this, I bet you guys buy there's 3 sig figs there, 3 here, 3 here. This brings no uncertainty, and that's an exact relationship too. So it looks like we're at 3 sig figs. So I got 8.11 times 10 to the 4th calories, or 81,100 calories. Which, if you left it, you know, we've talked about this in here, if you simply left it 81, that would work too, because 3 sig figs either way.
So if we get to like a test, and we have a question like this, I was always taught to do it as a ratio. And if we did it that way, like if I can't, because doing homework last night, I've been having so many problems. Remember, like I'll put 1,000 kilojoules equals 1 joule, and I keep switching it around.
Yeah.
So if I did it as a ratio first and then did it times the kilojoules and calories thing, or the joules to calories conversion, would it still be considered okay if I come out with the right answer, or do you want me to try and?
Yeah. I know exactly what you're saying, and the ratio is embedded in this, and it makes sense, you know, scaling up, you know, ratio. But for down the road, for all the chemistry problems that, you know, we're going to work for the next, you know, 12 weeks or so, 13 weeks, you really need to be using this method. So, but one thing I was thinking is if you do prefer the ratio method, one of the things you could do is use it to check. Like use your ratio method, see what the answer is, and then force yourself to go ahead and do it this way. So there's something to be said for that. But you're in very good company. You know, I see that in my, you know,
I know I'm not
chemistry
the only
students.
one.
What's that?
I know
No.
I'm not the only one that has that problem.
No.
'Cause I
It's
know a lot of
just
people who do.
It's just with ratio, the ratio approach, it just won't get you down the road, like I said, to working the more complicated problems. So, okay, so we already did this one. You guys handed this in. So let's take a look at the title of the next set. I think is more factor labeled. Like, really? I don't need more factor labeled. Okay. So here we're going to actually be doing some other things. That's more factor label. So we're actually going to be taking it up a notch. If we were to talk about area is length times width, okay? The area of something then usually has units of length squared. So we know that 1 yard in the English system is equal to 3 feet. Well, if you have 1 square yard, how many square feet do you have? And the next slide kind of tells you. So 1 square yard. So 1 square yard would be 1 yard by 1 yard. So it's 3 feet by 3 feet. And you end up with actually 9 square feet. So we're going to do that same problem, kind of factor label. Okay? So 1 square yard is 9 square feet, because each one of those boxes is a square foot. Okay. So we could do it this way. We could say if you know that you have 1 square yard, that's 1 yard by 1 yard, and each yard is 3 feet, okay, then actually we know we can grab those 3's, multiply them together, get 9. Grab the feet, multiply them together, get feet squared. 9 feet squared. Okay? That all works. Makes sense. Okay? But I'm going to kind of show you how, if you were faced with this sort of problem where you had units squared, okay, how do you handle that? And the answer basically is since it's units squared, you basically have to cancel the term twice, okay? So it's not too bad, okay? So if we do know, if our goal is to go from yards squared to feet squared, well, we know the relationship between 1 yard and feet is simply this. We know that 1 yard is exactly equal to 3 feet. We totally know that. But if there are yards squared, we basically have to introduce it twice to get those to cancel. Okay. Then, of course, you end up with combining the 3's to get 9 and combining the feet to get feet squared. So it's the same diff. So this would be working the problem kind of with the approach that we've said. We took an equivalency statement. We took an equivalency statement, 1 yard is equal to 3 feet. We turn it into conversion factor, made yards cancel, left with feet. Cool. So as you maybe know, on the previous slide, there were 3 terms there. The first term was 1 yard squared, and then basically you had 3 feet over 1 yard and 3 feet over 1 yard. We can collect those terms and square the outside. It's the same diff. It totally is. The problem with this that I run into personally is sometimes I forget that that square actually applies to the units and the number. It's really easy to use this and to not recognize that to stick it in your calculator, you got to recognize that that square applies to all units and all numbers. So this actually kind of shows you, reminds you of that. So again, a few slides ago, you could have just taken 1 yard squared times 3 feet over 1 yard quantity squared. That would be totally fine. Totally. So that was area, but in physical science, we're not as worried about area as we are volume. Okay? So let's take it up one more dimension. Okay? So remember, if we're talking about the volume of something that's cube-like, we take length times width times height to get the volume. So if we go back to the whole, like that Rubik's Cube back here, if we were to say, that'd be a big Rubik's Cube. But if we were to say that this is one yard by 1 yard, I guess it wouldn't be that big, it'd be pretty big, by 1 yard, okay? So how many feet cubed are there? Okay, because then each one of these is 1 foot by 1 foot by 1 foot. Oops, you know what I mean. Okay, so is this the next slide? This is weird. Okay, thanks. So actually, if we're going to do that conversion, we're going to have to take 3 terms of 3 feet over 1 yard. Okay, but now remember that if that's the case, you end up with this 3 cubed, which is what, 9? 3 times 3 times 5. Yeah, so it's 27. So you could basically take this whole thing is equal to this whole thing. Okay. Now, to me, I don't memorize. There's 27 cubic feet in 1 cubic yard. I do not. But I definitely would understand that there are 3 feet in 1 yard, and I can cube it if I need to. That would be just silly. Okay. Oops. So another way to think of it is if we have this equivalency statement, this is an exact relationship with regard to length in the English system, and we know that we need to cancel cubic yards and be left with cubic feet, we can go ahead and cube both sides too. That's a legitimate mathematical trick. Math has a lot of little tricks. Okay, so let's work a problem. Now this is, one way to look at problems is to right off the bat take a bird's eye look at it. So it looks like we're within the English system. Okay, we're going from inches cubed to feet cubed. That's not too bad, we should be able to do that. And we know that, you guys know that 1 foot is equal to 12 inches, so we're going to use that. Probably going to have to use that 3 times, basically. So that's it. There are different ways to kind of write the method for doing this, but basically we're going to go from that 22.0 inches cubed to feet cubed. So I would write the 22.0 inches cubed over 1. Again, don't forget that this 22.0 is a different number than 22. 22.0 is 3 significant figures, and that can play a part when we go to round it. Now you have some options. I can't remember how my builds are. I'm going to show you this option first. Basically, if we know we want to go from inches cubed to feet cubed, we know that with 1 time, 1 foot is exactly equal to 12 inches. And if we cube that, our cubic inches will cancel. We'll be left with cubic feet, which is great. This is just the deal, though. You need to recognize that this cube applies to that 12 too. And right up my head, what's 12 cubed?
That's okay.
144?
It's 144 times 140.
It's 1,728.
Yeah. 1,728. Thank you. Yeah, so it's 12 times 12 times 12. One more. Okay. So you guys know what we're doing here. So now notice we're allowed 3 significant figures because of the 22.0. But I probably wouldn't work it that way. I probably would, instead of this, what I have quantity cubed, probably when I work it, I would go ahead and expand out 1 foot over 12 inches times 1 foot over 12 inches times 1 foot over 12 inches. Because what that reminds me is that in the denominator, I need 3 factors of 12. So it's just up to you, as long as you do it right. Okay. So those are just other options of thinking about it. Did you guys get that answer? And you told me that was okay. Okay, another one with regard to volume. Now, inches cubed and liters, those sound so strange, inches cubed, but inches cubed is a volume, and liters is a volume, is a metric volume. Inches cubed is an English volume.
Centimeters cubed.
Right, exactly. So what I would suggest you do is basically anytime you have to do this, you're going to see on the next slide, but I would go through, really? I would go through centimeters cubed. Oops, sorry, darn it. Yeah, centimeters cubed. My IN looks like my CM. That's terrible, but this is inches cubed. So remember the one thing that I told you guys to remember? 1 inch is exactly equal to,
2.5.
yep, 2.54 centimeters, exactly. So basically, we're going to use this equality 3 times to get to centimeters cubed. And then how can we can't go from centimeters cubed right to liters, or not the way I said. We can go from centimeters cubed to milliliters. They're exactly equal, and then we can go to liters. Okay. So that's kind of how you're going to see me work the problem here. So again, we're going from inches cubed to liters, but we're going to go through centimeters cubed because we know that one. And then once we get to centimeters cubed, we say it has a 1-to-1 relationship with milliliters. 1 cubic centimeter is exactly equal to 1 milliliter. And then once we get to milliliters, we're ready to go to liters using the 1,000. Okay, if you're like me, though, I have to concentrate. 1,000 what? Well, actually, a liter is bigger, so 1 liter is exactly equal to 1,000 milliliters. So that's how we can knock this one out. So here we go. Start with inches cubed, 25.0 inches cubed. Whenever you never know, when you're struggling with how to start with the number that's kind of unique to the problem, which in this case, there was only one number given, 25.0 inches cubed. Put that over 1. Now I want my inches cubed to go away. I'm going to go to centimeters cubed. So I can either write 1 inch over I can either write 2.54 centimeters over 1 inch 3 times, or I can write 2.54 centimeters over 1 inch raised to the 3rd power. Like I said, the pitfall with this approach is you just got to remember that you have to cube your 2.54. Now, a good thing about this is if you run into one of these on homework or a test and you set it up right, but you just don't get it right in your calculator, then you definitely get a lot of the credit. So at that point, inches cubed are canceled. We're left with centimeters cubed. Now we're ready to go milliliters. So the next term would be 1 centimeter cubed. Oh, sorry. The next term would be 1 milliliter over 1 centimeter cubed. And then now we're ready for milliliters to cancel, so we'll go, 1 liter over 1,000 milliliters. And we should be done. So like I said, my favorite part is canceling my units. Inches cubed are canceled, centimeters cubed are canceled, milliliters have canceled, and we have units of liters, which are terrific. There is no uncertainty brought by the milliliter centimeter relationship. There's no uncertainty brought within the metric system. And remember, that whole centimeter inch thing, that is exact. So there's no uncertainty brought there either. So looks like 3 sig figs. So actually in this case, to show 3 significant figures, we do need a trailing 0 after the decimal. So it's not 0.41, it's 0.410. Show 3 significant figures. No naked numbers, units, or liters. What do you think? Okay. So, not 289, but 287, 292. So chapter 2, problems 87, 92, and 105. So we'll take a look at those right quick. Now I haven't looked at them for a year, so here's 87. And it's kind of like the homework that you handed in today. You have to use the factor label method. So just if we kind of take a look at the first one together. Okay, so our first term is going to be 1.0 kilometers over 1. And so flat out, probably if I was working this in my answer key, flat out, I would write 1 kilometer is exactly equal to how many meters?
1,000.
Yep, 1,000. I would even write that equivalency statement somewhere. Because now, when I go to use it, okay, I know that I want kilometers to cancel. I'm left with meters, so what goes there? There's here 1,000 meters over 1 kilometer. I think one of the things that we don't do is take our time with problems sometimes. I'm like, we kind of get in a hurry. But, oh, my bad. Look, I needed a square, the thing I'm trying to convert. So now, what do I got to do with that second term?
Either square or put it twice.
Yep, either square it or put it twice. Perfect. I'll just go ahead and square it. Okay, I think I should be fine with that. All right, the next one. A classroom has a volume of 285 cubic meters. What is this volume in cubic kilometers, in cubic decimeters, and cubic centimeters? Now, deci is 1/10 of. So I'll kind of leave that for you guys. Use factor label. And the last one, a block of metal has a volume of 13.4 inches cubed. and weighs 5.14 pounds. Okay. And we could draw a picture, but I think I'll not do that for you. But the question here is, what is the density in grams per cubic centimeter? So question mark. What is the density in units of grams per centimeter cubed? That's kind of hitting you over the head with what we're trying to get. So you guys did density problems. You did really pretty darn good with density problems. So the density here is given in 5.14 pounds, mass divided by volume. The volume is 13.4 inches cubed. Okay, I could go ahead and knock out on my calculator. The thing is, I would get units of mass in pounds and units of volume in inches cubed. But my goal is to get units not in mass, not in pounds, but grams. The goal is to get not volume in inches cubed, but in centimeters cubed. So we have a couple of options. Probably when I do this as an answer key, I would probably just kind of fix my density right then and there. Okay, so for instance, if I want to go from grams to pounds, is that something you're supposed to memorize? Is that something that I would give you on a test? Yeah, so that little table of grams and pounds is like 453 or something grams in 1 pound. It's an approximate relationship. You can do that. So I would look up how these are, what the equality is between these. To go from centimeters cubed to inches cubed, we did that, something like that today. Okay, so actually I would probably have a couple of terms down here to get to grams per centimeter cubed. Okay, was that it? Okay, so I think that's probably enough for today. We'll pick up here on Friday, so we're in pretty good shape for your test next Thursday.
For the homework that I'm gonna be going for, what do you